You're tracking down a sudden network outage. You pull up the device logs to find out exactly what failed and when, only to see every entry stamped with a date from 1993. Without accurate timestamps, piecing together a sequence of events across multiple routers and switches is impossible. If we look at this top block of messages, we can see these syslogs are marked June 18th. If an error happens across 3 different devices, we need these times aligned down to the millisecond to trace the root cause. In this walkthrough, we will configure the precise time, set the correct geographic time zone, and synchronize the internal hardware calendar on a Cisco iOS device. To follow along, you need command line access to your router or switch, and you need to be in privileged exec mode. Time accuracy secures your network. It ensures cryptographic certificates are valid, audits are reliable, and your troubleshooting logs actually point you to the problem. First, we check our baseline. In your terminal, type Show Clock Detail to see exactly how the device currently understands time. Looking at this output block, there is an asterisk sitting right before the timestamp. That asterisk means the time is currently unauthoritative. It is relying entirely on the default hardware calendar, which has not been synced to an external source. Before we set the time, we must set the time zone. If you manually set the clock first, then apply an offset, the system shifts your correct time by several hours, throwing your logs out of alignment. To set the time zone, move into Global Configuration mode. Here are the exact syntax lines we need. Clock time zone, followed by the name of the zone, and its offset from UTC. Next, we account for daylight saving time. We use the clock summertime command. Typing a question mark prompts us for the exact recurring parameters. We follow the prompts to define when clocks spring forward and fall back, establishing a complete recurring schedule. By establishing the region and seasonal rules first, any manual time adjustments we make next will remain accurate throughout the entire year. Back in privileged exec mode, we initiate manual time configuration by typing clock set, followed by the current hours, minutes, and seconds. The system then asks for the date. Hitting enter submits the carriage return, signifying the router has accepted the new time. But there is a structural detail to understand here. Cisco devices maintain 2 completely independent clocks. There is an active software clock running in the operating system and a physical, battery-backed hardware calendar sitting on the motherboard. Right now, we've only updated the software clock. If the device loses power and reboots, it reads the old time from the physical motherboard battery, overwriting the accurate time we just entered. To prevent that, you can manually configure the hardware clock with the calendar set command, or simply use clock update calendar to permanently stamp your active software time onto the physical battery. If you ever need to do the reverse, pulling the hardware time up into the software, you use the clock read calendar command. Synchronizing the volatile system memory with the physical motherboard ensures the router maintains a consistent, accurate timeline, even through a complete power failure. Let's verify our configuration. Run Show Clock Detail one more time. The asterisk is gone, and our local time zone abbreviation is now present. The system logs are completely authoritative. However, physical components degrade. Over time, the internal quartz crystal will drift. Logging into hundreds of enterprise routers to manually correct that drift is impossible. This is where Network Time Protocol, or NTP, takes over. Using UDP port 123, NTP constantly queries highly accurate time servers on the internet and automatically corrects the internal clocks across your entire infrastructure. Looking at this diagram of the NTP hierarchy, devices are organized by stratum levels. Stratum 0 represents atomic or GPS reference clocks. Stratum 1 servers connect directly to those reference clocks, and lower-level stratum servers pull their time hierarchically down the chain. Configuring the clock manually ensures a single router has a stable baseline, but implementing NTP is the architectural standard required to keep an entire global network operating on the exact same millisecond.